Coding a Mecanum drive is a fundamental step for most FTC teams, but getting it to drive intuitively is a major hurdle for a lot of them. By the end of this video, you'll have a clean, reusable Java class for your Mecanum chassis, and you'll understand how to implement both robot-orientated and the far simpler field-orientated control. I'll also explain what both those terms mean if you have no idea what I just said. This skill will make your code easier to manage, and it will make your driver's life so much easier on the competition field. I'm Coach Pratt, and for over a decade, I've taught robotics and design. I've coached FTC teams to national championships and multiple Inspire Award wins. I've seen firsthand how a solid, easy-to-control drive program is an absolute foundation for your drive team finding success out on that field. Today, I'm going to walk you through the entire process. We'll start with the basic Mecanum calculations, then build a dedicated drive class, line by line, and finally we'll put it all together in your main op mode so you have a fully functional and understandable drive program. So let's talk quick about what a robot-centered orientation means. So typically on a Mecanum chassis, you have driving forward, strafing left and right, and then rotation with this joystick. So when I talk about driving forward, this would obviously be forward and reverse for the robot. On my robot here, I've got human player, and this little triangle or this arrow is the direction that he's currently facing. If I were to strafe left and right, it is going to move the robot to the right and to the left, respectively. And if I were to rotate this around, it's going to rotate our robot around his center axis, like so. Now, in a robot relative or a robot orientation, what happens is if, let's say for imagination, we've got this field over here, and we have a robot facing in this orientation, and the human player is facing in this orientation. So the human player is facing the same way. Over here, when we pressed forward, the robot followed its forward position. Here, when we press forward again, this is now the forward direction, and this is now the reverse direction. And then so on and so forth, strafing left and right. This would be strafe left, and this would be strafe right because it is the left side of the robot. Now, the rotation still works as we would expect, and that's not really going to change. Where this really starts to get confusing is if your robot is in the downward position, because now if you are still facing forwards, this is forward, this is reverse, this is right, and this is left, except that would move your robot right, that would move your robot left, move your robot down, and move your robot up relative to the field. So this is sort of a robot orientation. Now, some people prefer this kind of code, but this kind of code is a building block to be able to get us up to a field-orientated system, which is what I'd suggest most teams go on instead. So rather than a robot orientation, we talk about a field orientation, it's more like this. So we'll go back to the same scenario. We've got the human player, and they're facing in this direction. And we have a robot, and let's say the robot is facing backwards. When it is field relative, or a field orientation, spelled relative wrong there, when I press forward, regardless of what direction the robot is facing, we're going to move this way. And when I strafe to the left, regardless of what direction the robot is facing, it's still going to strafe to the left. And respectively strafe to the right and move in reverse as that human would expect. So it does make things a lot simpler for moving a robot around to have things field relative, because now it's always based on the direction that you are facing rather than the direction that the robot is facing. So that's what I highly suggest you do. And that's what we're going to learn how to do today. Now, in the example that we're running through today is actually made coming from the first SDK in the examples folder. This is down in the robot TeleOp Mecanum relative field drive. So we're just going to go through this example today. And I'll do a little bit of explaining as we go, and we will go through typing this together. But if you're curious where we found that code, you can go ahead and find it from that section there. I always like to set up my code with different mechanisms being in different packages. I think that makes life a lot cleaner. It makes your main code a lot cleaner. Instead of having to run through your entire op mode with a whack load of code inside of it, you can just make it significantly cleaner. So inside my team code, I always like to make a new package. And the package I call the mechanisms folder. And inside this mechanisms folder, we're going to make a new class. And we're going to call this one Mecanum Drive. So inside here, we're going to have 4 DC motors. We're going to make a private DC motor. And we have a front left motor, a back left motor, a front right motor, and a back right motor. Oh, let's go away. Back right motor. In this is a nice little trick you can use if all of your variables in Java are going to be the exact same type, in this case a DC motor, you can just put commas and we'll put them all in the same. Oops, the back right should be capitalized. Now we need to actually initialize these motors or be able to create a method that's actually going to initialize them to assign a value, because right now they don't really mean anything. So we're going to make a public void method called init. And this is going to take a hardware map as an argument. And now we're actually going to create our 4 motors. So our front left motor is going to be equal to, go away please, hardware map dot get, and this is going to be a DC motor dot class, comma, and then inside of a string, we need to put in the exact name that we've written inside of the driver station for that front left motor. So in my case, I've called it front left motor. Some people call these front left drive. Whatever it is you have called it, you need to make sure that that is what you have written inside of your config file, or this will not work. Then we're going to have our back left motor is equal to hardware map dot get. Same thing again, DC motor dot class, and this is the back left motor. Then we have our front right motor is equal to hardware map dot get. And we have, again, DC motor dot class. And this one is the front right motor. And then we have the back right motor is equal to hardware map dot get. Again, DC motor dot class and back right motor. Now, for most Mecanum drives, when you set up your motors, you don't have them in this orientation. You've actually got them mirrored for one another, which means that if you send one of your motors positive, the other side is actually going to be moving in reverse to how your other motor is moving. In order to get them moving in the same direction, you're going to have to reverse them. And typically, we reverse the left-hand side of that drive. So we are actually going to take our front left motor dot set direction, and our direction is going to be in reverse. I love autocomplete in Android Studio because it stops me from having to write DC motor dot direction dot reverse. Saves a ton of time. So again, we're going to do the same thing for the back left motor dot set direction. And again, it's going to be direction dot reverse. And that's not DC motor simple, it's just DC motor. Next, I highly suggest you use encoder wires on yours. And we're going to set each of these motors to be running in the encoder mode. You can have them run to position versus run to encoder. Run to position is basically going to try to run until it gets to a specific encoder position. For drivetrain motors, I like to use run to encoder, because what that does is it makes all of your motors try to achieve the specific speed or velocity that you've told them to move at. So it means that if you have them all trying to move at a 50% velocity, regardless of how much friction is being placed on that motor, it's going to use its internal PID controller to be able to try to move at 50% speed, and it's going to change its power to be able to do that. So we're going to say front left motor dot set mode, and this is going to be run mode, run using encoder. We're going to do the same thing for all of them. So the front left motor, the back left motor dot set mode, and it's going to be run using encoder. Our front right motor dot set mode is going to be run using encoder, and our back right motor dot set mode is also going to be run using encoder. Now, if we were doing a robot-orientated drive at this point, we'd be done. But because we're doing field-oriented, we're going to use the built-in IMU on the rev hub to be able to handle this. So we're going to go back up to the top where we had our private DC motor. We're going to make a new private called IMU, and it is going to be an IMU class. Or sorry, a variable is going to be IMU. Then down here, we're going to say that IMU is equal to harbor-map.get, and it's going to be an IMU.class. And then for, as long as you have not changed this, you shouldn't have to change anything in your configuration file. It should be named IMU. And then next we have to set the orientation of that rev hub. The orientation of this rev hub relates to the logo you have on the robot and where the USB drive is facing on that robot. So right now in this orientation, if my robot were facing in this direction and this is placed as it is on top of the robot chassis, this would be logo facing up with USB-C facing forward. If I had it placed on my robot like this, it would still be logo up, but my USB would be facing in reverse or backwards. You are allowed to have this thing facing to the side. You could have it facing upside down. The one thing I'd recommend that you do is you set this up square on your robot. So you want to have it in a square angle. You don't want to be setting this thing up on a weird angle because that's just going to make life a lot harder. You can do it, but it's just going to have to add in some extra programming when you realistically could set this thing up in a square orientation and you don't have to do any extra calculations to account for that. So back in Android Studio here, we're going to go ahead and set what its orientation is going to be. So we're going to say the rev hub orientation on robot, the rev orientation is going to be equal to a new rev hub orientation on robot. I'm going to put a new line in here because it starts to get very, very long. The first thing it's going to ask for is a logo facing direction. And in our case, our logo facing direction is up. I'm putting a comma, put in a new line. After you set the logo orientation, it's going to ask you for a USB orientation. So this is going to be a rev hub orientation on robot dot USB facing direction dot, in this case, it is forwards. And then we can go ahead and finish that line off. And I might bring that back just so it makes it a little bit more clear there. So now we've set up orientation. We can go ahead and initialize that IMU. We're going to write IMU.initialize, new IMU parameters, and then inside of this IMU parameters, we're going to put in our rev orientation. We're going to start by making a method for driving in robot orientation, and then we're going to make another method that's going to recorrect those values that we're going to send to that robot orientation into a field orientation robot. Now, this little section comes from an FTC team. It is 16072. So thanks for them. And that's also pretty cool that they're able to get some code inside the official SDK. That's really neat. So we're going to make a new public void called drive. And drive is going to take 3 arguments. Take a double called forward, a double called strafe, and a double called rotate. So of course we have our forward power, our strafing power, and then our rotation power. Next, we're getting into some fancy mathematics where effectively there is some simple mathematics equations you can use that will make Mecanum drives work. If you're curious about how exactly these mathematics work, I've got a full video in the description down below, but the physics behind this. Otherwise, we'll just go ahead and put in these equations. So we'll say front left power is equal to forward plus strafe plus rotate. Our back left power is equal to forward minus strafe plus rotate. Our front right power is equal to, not minus straight, minus strafe. So our front right power is equal to forward minus strafe minus rotate, not strafe minus rotate. And I still can't spell strafe properly. And then our back right power is equal to forward, plus strafe minus rotate. Next, we have to set in a constraining section. We're going to say a new double called max power is going to be equal to 1.0. We're going to use this later so we can constrain all our values back down, because you can imagine that there's a scenario where I'm pushing all of my joysticks where I'm setting the value of 1 to both forward, strafe, and rotate. If you add those three of those together, you get 3. And if you were just send a command of 3 to your motors, it's actually going to pull it back down to a value of 1, which means if you do not clamp or constrain and normalize all of your values back down, that one of the motors should be 3 times as powerful as the other motors, then you wouldn't actually have the correct calculations. Now, I like what this team did, so that's what max power is going to do. I also like what this team put in here, where they put in a max speed. If you're only going to be running your robot for competitions, there's no need to put the max speed in. But what this allows them to do is if they go onto outreach events, they can set it to like 0.3. So if they're having young children driving their robot around, they don't have to worry about them moving around at its full max speed. And then when they're ready to go back competition, they just have to change back this one variable. So that's a really slick little trick. So now we're actually going to take some time. We're going to redefine max power 4 different times. So max power is going to be equal to math.max of either max power or math.absolute of our front left power. Then we're going to take max power and we're going to reassign it again to math.max, whichever one is higher between the previous max power and math.absolute of the back left power. And the same thing again, max power is going to be equal to math.max of whatever the previous max power was, and math.absolute of the front right power. And then again, one more normalization here of math.max of whatever the previous max power was, and math.absolute of the back right power. So what this is doing is it's saying, okay, your max power is 1. Let's check. Is front left power higher? If it is, reassign max power. And now we're going to grab that new one. And we're going to see which one has the absolute max power. So we can see what is the ratio we need to scale everything else down on so we know how fast we can send individual ones. Now we can actually go ahead and set our values. So we're going to say that our front left power, our front left motor dot set power is going to be equal to max speed multiplied by front left power divided by max power. And we'll do the same thing for all the other ones. Again, if you're not going to be using this for outreaches, you don't need to bother putting in that max speed, but that's just going to constrain your values. So now we're going to have our back left motor dot set power is going to be equal to max speed multiplied by the back left power divided by max power. Our front right motor dot set power is going to be equal to max speed multiplied by our front right power divided by max power. And then our back right motor dot set power is equal to max speed times our back right power divided by max power. And this is where you're actually finally going to send out those robot commands. So if you were happy with having robot-orientated drive, you could just finish this off now and just use your drive, and your Mecanum chassis would drive as you would expect. But I highly suggest that you don't use robot-orientated driving, because field-orientated driving is much more natural, and driving is already hard enough for your drivers. They're already stressed enough when they're on that field that having robot-orientated is going to make life a lot easier. So we'll make a new public void called drive field relative. And this is, again, going to take 3 arguments. It's going to take a double of forward, a double of strafe, and a double of rotate. So we're going to go back to Alan Smith's excellent book here on Learn Java for FTC to talk about this really quick. Typically, we're working Cartesian coordinates with X and Y plotting, but in order to do field orientated, we have to go back to a polar coordinates, which you may have seen these. This is related to like a radar system or things like that. So rather than using X and Y to be able to plot our position, you end up with an angle theta, and R is your distance away from your center point. And then thankfully, you can use a little bit of simple mathematics that is already baked in for us, thankfully, with a little bit of trigonometry to be able to turn our Cartesian coordinates into a polar coordinate. Let's go ahead and let's convert that theta, our X and Y position, into polar coordinates. So we're going to make a new double called theta is going to be equal to math.arctan or atan2. And we're going to put in our forward and our strafe. And then we're going to have to grab that distance. So it's going to be double R is going to be equal to math.hypotenuse of strafe and forward. Next, we have to rotate the angle so we get the angle the robot's actually pointing at. And we'll use the IMU to do that. So we'll say that theta is equal to angle unit dot normalized radians theta minus, we'll put this in a new line, it's about to get a little long, IMU dot get robot yaw pitch roll angles dot get yaw. And inside this get yaw, the angle unit is going to be radians. So this is going to get our current angle, and then it's going to rotate theta based on where the robot's actually facing. So next we have to convert those polar coordinates back into Cartesian coordinates. So we're going to make a new double called new forward. And we're going to say that our new forward is equal to our distance times math.sine of theta. And we have a new strafe is equal to the distance times cosine of theta. And then lastly, we're going to call our drive again. So this dot drive is going to be, and then it again has the 3 ones. We have new forward, new strafe, and then rotate, whatever that was called. So this is what's actually going to call our robot to be driving in field-orientated drive. So now that we have the class set up, let's go ahead and put this into an op mode. So inside our team code, we're going to make a new Java class. We're going to call this Mecanum field-orientated OpMode. And this one is going to extend the OpMode class. And inside OpMode, we always need 2 classes. We always need 2 methods. We need a public void init, and we need a public void loop. So in here, we're going to go ahead and create a new instance of that the Mecanum drive that we just created. So we're going to say that Mecanum drive is equal to a new Mecanum drive. And then because in that Mecanum drive, we made that initialization method to be able to tell all of our hardware where it is inside of the control hub, we're going to go ahead and create that. So we're going to say our drive.init, and we're going to call it in the hardware map. Below this, we're going to make 3 new variables here. We're going to make a couple doubles. We're going to have a double for forward, for strafe, and for rotate. Again, we use that little shortcut because they're all doubles. Then inside that loop, we're going to say forward is equal to gamepad1 dot left stick y. Our strafe is equal to gamepad1 dot left stick x. And our rotate is equal to gamepad1 dot right stick x. Again, because robots are sensing, thinking, acting machines, I always like to do all of my sensing up at the top. assign them in variables, and then work with those variables later. I think it makes life a lot simpler and that you're not having to reread things all the time in your loop. Then I'm going to go ahead and call drive.drive. Sorry, actually, we're going to drive field relative, and we're going to pass it in forward, strafe, and rotate. And that's it. That's how you can get your robot driving field orientated so that you can always have wherever you are facing, that's the direction that it's also going to go. I hope you found that helpful. If you have more questions, let me know in the comments down below. If you want to do a little bit of further reading and further learning, of course, the examples here in the SDK for FTC are excellent, as is Alan Smith's excellent book on Learn Java for FTC. I'm going to have links to both of those in the description down below. If you have any more questions, let me know, and I'll try my best to help you out in the comments. Otherwise, best of luck out there this season, and I hope to see you out there.